Before we get into today's video, I want to share a sincere apology with all of you. As I've mentioned in my previous updates, my health hasn't been the best lately, which is why I haven't been able to provide my own voiceover for the videos I create. Over the past few days, I've had to undergo a series of medical checkups and tests, which unfortunately kept me from posting new content for a while. I truly appreciate your patience and your understanding during this time. Now, without further ado, let's dive right into today's main topic. Chapter 1. The Birth of the Quark Star. 1. The Theoretical Titan. Deep within the cosmic hierarchy, there exists a ghost in the equations, the Quark Star. While neutron stars have long been considered the densest objects in the universe short of a black hole, theoretical physics suggests a state of matter even more extreme. A quark star is a theoretical celestial body that pushes the boundaries of reality, packing a mass greater than our sun into a sphere no larger than a city, with a density that defies conventional physics. 2. The process of deconfinement. The birth of this star is a story of ultimate pressure. Inside a massive neutron star, gravity is so relentless that it overcomes the strong nuclear force holding particles together. This leads to a phenomenon known as deconfinement. Neutrons are literally crushed until they dissolve, releasing their inner components, quarks, into a dense, fluid-like primordial soup of quark matter. According to the Bodmer-Witten hypothesis, this strange matter might actually be the most stable form of matter in the universe. 3. A mirror to the Big Bang. To see a quark star is to look back 13.8 billion years. Approximately 1/1,000,000th of a second after the Big Bang, our entire universe was in this exact state, a Quark-Gluon plasma, or QGP. Data from the Large Hadron Collider at CERN has confirmed that at temperatures trillions of degrees hot, protons and neutrons cannot exist. Instead, quarks and gluons roam free in a frictionless, perfect liquid. A quark star is, in essence, a living relic of the dawn of time. 4. The Cosmic Lockdown. As the early universe expanded and cooled, it underwent a phase transition. This was the Great Freeze of the subatomic world. The cooling allowed the strong force to take hold, permanently imprisoning quarks inside larger particles like protons and neutrons, a state known as color confinement. They have remained locked away ever since. However, inside the heart of a quark star, gravity reverses this process, unlocking the cage and bringing the primal state of the universe back to life. Chapter 2. The Cosmic Time Capsule. 1. A state that never ended. In the mainstream model of the universe, the chaotic quark era ended almost as soon as it began. But what if that wasn't entirely true? Theoretical physicists, including those studying the Tolman-Oppenheimer-Volkoff limit, suggest that in the most extreme environments in the cosmos, the cores of ultra-massive stars, this primordial state might have never ended. Inside these gravity-defying giants, the conditions of the early universe aren't just a memory. They are a living, breathing reality, sustained by pressures we can barely calculate. 2. The 13.8 billion-year-old time capsule. If a quark star exists, it is the ultimate cosmic time capsule. Locked away within its heart is a form of matter that hasn't existed freely since the Big Bang, 13.8 billion years ago. This is known as the Bodmer-Witten hypothesis, which proposes that quark matter is the true ground state of matter, more stable than the atoms that make up our bodies. In this sense, a quark star is a relic of the ancient past, perfectly preserved and sealed away by the insurmountable fist of gravity. It is a piece of the beginning of time, hidden right in front of our telescopes. The universe's greatest secret. To truly grasp the significance of a quark star, we must confront the mystery of how the cosmos hid its earliest moments. During the transition from the Big Bang to the present, the universe underwent what we call symmetry breaking, forcing quarks into permanent exile within protons and neutrons. By studying quark stars, we are attempting to look behind the curtain, to understand the raw, unfiltered energy that defined the first microsecond of existence. It is a journey to uncover the secret history that the universe has spent billions of years trying to conceal. Chapter 3: The Inferno of the Primal State. 1. The millionth of a second. To understand the environment of a quark star, we must travel back to the most violent epoch of our history. Just 1/1,000,000th of a second after the Big Bang, the universe was a place of unthinkable extremes. At this precise moment, the ambient temperature of the entire cosmos soared to a staggering 2 trillion degrees Celsius, 3.6 trillion degrees Fahrenheit. This wasn't just heat, it was a cosmic furnace that redefined the laws of matter. 2. Defying the heart of the sun. To put that into perspective, this temperature is approximately 130,000 times hotter than the core of our sun. In this inferno, the laws of nuclear physics as we know them completely break down. According to models supported by NASA's Goddard Space Flight Center, the heat was so intense that it was impossible for any composite particle to remain stable. Protons and neutrons, the very building blocks of the world we see today, simply could not hold together. They melted away into their most fundamental components. 3. The perfect liquid. What remained was the primordial soup, a state known as Quark-Gluon plasma. In this ultra-hot, frictionless fluid, quarks wandered freely, unbound by the forces that normally lock them away. This is the most basic and primitive form of matter in existence. As confirmed by experiments at the Relativistic Heavy Ion Collider, RHIC, this plasma behaves like a perfect liquid, and it is this exact raw material that is believed to be resurrected deep within the crushing heart of a quark star. Chapter 4: The Breaking of the Cosmic Rubber Band. 1. The Elastic Paradox. At the heart of all matter lies a force so strange it defies common intuition: the strong nuclear force. Unlike gravity or electromagnetism, which get weaker with distance, the strong force does the opposite. It behaves like a cosmic rubber band. The further you try to pull quarks apart, the harder the force snaps back. This phenomenon is scientifically known as color confinement. It is the reason why, in the natural world, a solitary quark has never been observed. 2. 13.8 billion years of imprisonment. Because of this confinement, quarks have been effectively condensed, trapped inside protons and neutrons since the cooling of the Big Bang. For 13.8 billion years, this subatomic prison has remained unbroken. Quarks are social creatures by necessity. They must exist in groups of 3 or pairs, hiding their color charges from the rest of the universe. This stability is what allows atoms, stars, and even ourselves to exist. 3. The might of gravity. But there is a way to break the unbreakable. While even the highest temperatures often fail to liberate quarks, the extreme gravity of a collapsing star can. Inside the heart of a potential quark star, the pressure becomes so immense that it overcomes the energy of the rubber band. When matter is squeezed beyond the density of an atomic nucleus, quarks are forced so close together that their individual boundaries begin to blur. Gravity essentially snaps the bond of confinement. 4. Asymptotic freedom. This leads us to one of the most profound discoveries in modern physics: asymptotic freedom. This Nobel Prize-winning theory, pioneered by physicists like David Gross, Frank Wilczek, and David Politzer, explains that at extremely short distances, or under extreme pressure, the strong force actually weakens. The quarks become effectively free within the star's core. In this state, the star recreates the conditions of the universe's birth, using pure gravitational power to achieve what was once only possible in the Inferno of the Big Bang.
Chapter 5. From Theory to Reality. The Quest for the Quark. 1. The Great Displacement. The story of the Quark Star is one of cosmic recycling. The ancient matter that defined the universe's first moments didn't simply vanish into the void. Instead, it was displaced. This primal energy transitioned from the vast, expanding reaches of the early cosmos into a compact, ultra-dense celestial body, often no more than 15 miles, 24 kilometers in diameter. Inside this small sphere, the history of 13.8 billion years is compressed into a single, extraordinary point of existence. 2. The naming of a mystery. Before we could look for quark stars, we had to discover the quark itself. In 1964, physicist Murray Gell-Mann, a giant in the field of particle physics, proposed a revolutionary model to bring order to the particle zoo, a chaotic collection of over 100 subatomic particles discovered at the time. He sought a name that was as peculiar as the particles themselves, finding inspiration in a line from James Joyce's novel Finnegan's Wake: 3 quarks for muster mark. Gell-Mann's theoretical framework, which earned him the Nobel Prize in 1969, suggested that everything we thought was elementary was actually made of something much smaller. 3. The Stanford Breakthrough. For years, quarks were seen as mere mathematical abstractions. That changed in 1968 at the Stanford Linear Accelerator Center, SLAC. In a series of groundbreaking experiments known as deep inelastic scattering, scientists fired high-energy electrons at protons. They expected the electrons to pass through or bounce off a solid core. Instead, the way they scattered proved that protons were not solid spheres. They contained 3 distinct point-like concentrations of charge. These were the quarks. This discovery didn't just prove Gell-Mann right, it provided the empirical foundation that makes the existence of quark stars a very real possibility in the eyes of modern science. Chapter 6. The Cosmic Tug-of-War. 1. The Weight of a Mountain. To appreciate the leap from a neutron star to a quark star, we must first look at the sheer insanity of neutron matter. A single teaspoon of a neutron star's surface would weigh approximately 1 billion tons. Imagine taking the entire mass of Mount Everest and crushing it down until it fits inside a single sugar cube. This is the density of the atomic nucleus itself, spread across an object the size of a city. At this stage, there is no more empty space left in matter. It is as solid as the universe allows. Or so we thought. 2. The breaking point, the TOV limit.
Every celestial object has its breaking point. For neutron stars, this is defined by the Tolman-Oppenheimer-Volkoff limit. According to calculations rooted in general relativity, if a star's core exceeds roughly 2.1 to 3 times the mass of our Sun, the neutron degeneracy pressure, the quantum force keeping the neutrons apart, finally fails. Gravity, relentless and patient, winning the battle, begins the final crush.
3. Two paths of destiny. At this critical threshold, the star faces two possible destinies. The most common path is a total collapse into a black hole, where matter vanishes behind an event horizon. However, there is a second, more exotic exit, the Quark Star. If the quark degeneracy pressure, the repulsion between freed quarks, is strong enough, it can halt the collapse. It creates a stable, ultra-dense hybrid that sits on the razor's edge between a standard star and a gravitational singularity.
4. The ultimate tug-of-war. Ultimately, a quark star represents the most extreme tug-of-war in the cosmos, pitting the absolute crushing power of gravity against the fundamental laws of quantum mechanics. This journey of discovery, which takes us to the very limits of reality, actually begins with the familiar. By understanding the simple density of iron, or the atoms in your own hand, we can begin to grasp the staggering complexity of these cosmic titans. The universe isn't just stranger than we imagine, it's stranger than we can imagine.
Chapter 7. The Illusion of Solidity. 1. The weight of reality. To truly grasp the incomprehensible power of a quark star, we must first look at something familiar, something we can touch and feel. Consider a simple block of iron. With a density of 7.87 grams per cubic centimeter, iron feels solid, unyielding, and heavy in your hand. For thousands of years, we have relied on this density to build our world, perceiving it as the very definition of solid matter. 2. The Great Deception. But science reveals a startling truth. Matter is an illusion. If you were to zoom in on an iron atom, you would find that it is, in fact, 99.9999999% empty space. According to the Rutherford gold foil experiment, which revolutionized our understanding of atomic structure, the nucleus is infinitesimally small. To visualize this, if an atom were expanded to the size of a professional football stadium, the nucleus would be no larger than a small marble sitting at the 50-yard line, while the electrons would be like tiny gnats buzzing in the highest seats of the stands. Grasping the void. When you hold a piece of iron, you aren't holding a solid object. You are holding a vast, organized nothingness. The sensation of solidity you feel isn't from particles touching, but from the intense electromagnetic repulsion between electron clouds. Between the central nucleus and those distant electrons, there is absolutely nothing, just a profound vacuum. Understanding this hollowness of everyday matter is the only way to appreciate the terrifying reality of a quark star, where gravity finally wins the war against the void, crushing that empty space out of existence.
Chapter 8. White Dwarfs and the Quantum Shield. 1. The first step into the extreme. To understand the crushing depths of a quark star, we must first look at the cosmic corpses known as white dwarfs. When a star like our Sun exhausts its nuclear fuel, it sheds its outer layers and collapses into an object roughly the size of Earth. This is the universe's first major step into extreme compression. Here, matter is so dense that it no longer behaves like a gas, but like a solid crystal of nuclei submerged in a sea of electrons. The only thing preventing total collapse is a bizarre quantum phenomenon called electron degeneracy pressure.
2. The Pauli exclusion principle. This pressure isn't caused by heat, but by the laws of subatomic physics. According to the Pauli exclusion principle, a cornerstone of quantum mechanics, no two electrons can occupy the same quantum state simultaneously. When gravity tries to crush the star further, these electrons resist with a violent force, effectively acting as a quantum shield that holds back the weight of an entire star. At this stage, a single cubic inch of white dwarf material would weigh as much as a heavy truck here on Earth.
3. The Chandrasekhar limit. But even this quantum shield has a breaking point. In 1930, while sailing from India to England, a young physicist named Subramanian Chandrasekhar calculated the ultimate limit of these stars. He discovered that if a white dwarf's mass exceeds 1.44 times the mass of our Sun, the electron degeneracy pressure is simply not strong enough to win the war against gravity. This threshold, now known as the Chandrasekhar limit, is the point of no return. Once crossed, the electrons are defeated, and the star is forced to collapse even further, descending into the even denser and more terrifying realm of neutron stars. Chapter 9. Neutron Stars. The Death of Empty Space. 1. The End of the Atomic Void. When a star crosses the Chandrasekhar limit, it enters a realm of density that defies imagination. In a neutron star, the vast empty space that once defined the atom is completely obliterated. The electrons are forced to merge with protons, creating a star composed almost entirely of neutrons. Imagine the stadium we spoke of earlier. The entire structure has been crushed until the stadium itself is no longer than the marble at its center. In this state, atomic nuclei are no longer separated by a vacuum. They are touching, edge to edge, forming the densest material in the known universe.
The weight of a continent. The resulting density is nothing short of terrifying. As confirmed by NASA's Neutron Star research, matter here is packed so tightly that a single teaspoon of this material would weigh approximately 1 billion tons, roughly the equivalent of taking the entire mass of Mount Everest and squeezing it into a space the size of a sugar cube. This is the absolute final frontier for what we consider normal matter. It is a world governed by neutron degeneracy pressure, a quantum wall that represents the last line of defense before the star either stabilizes or surrenders to the ultimate gravity of a black hole.
Chapter 10. Quark Stars. The Last Stand Before the Abyss. 1. The Final Shattering. If gravity continues its relentless assault, even the mighty neutron star must give way. When the pressure surpasses the strength of neutron matter, we witness the final shattering of the atomic world. The neutrons themselves are crushed, their boundaries dissolve, and they undergo a phase transition into a deconfined state. What remains is a quark star, a completely homogeneous celestial body where the distinction between particles disappears. In this state,
The star becomes a giant singular atomic nucleus, a sphere of pure liquid-like quark matter sitting on the very precipice of a black hole.
2. The mathematical void, the equation of state. But here we reach the limits of human knowledge. To describe how a star behaves at these densities, scientists need what is called an equation of state, EOS, a mathematical bridge between pressure, temperature, and density. However, at the heart of a quark star, our current tools are neutralized. The laws of quantum chromodynamics, QCD, the physics governing quarks, become incredibly difficult to solve in such dense environments. Because we cannot yet replicate these conditions in a laboratory or solve the complex many-body equations involved, the internal structure of a quark star remains one of the greatest unsolved mysteries in modern astrophysics. 3. The last barrier. A quark star is the universe's last attempt to maintain a physical presence before gravity claims everything. It is a strange stability that defies our standard models. According to researchers at institutions like CERN and the Perimeter Institute, if this final line of defense fails, the star will vanish behind an event horizon, leaving no trace of its existence. The Quark Star is the ultimate survivor, a beacon of matter standing tall against the absolute darkness of a gravitational singularity.
Chapter 11. The Living Legacy of Genesis. 1. A Laboratory of Genesis. Ultimately, a quark star is far more than just a theoretical celestial body. It is a cosmic sanctuary, a natural laboratory that preserves the raw, chaotic state of the universe at its very birth. By holding matter in a state that existed only 1/1,000,000th of a second after the Big Bang, these stars serve as a bridge across 13.8 billion years of history. They allow us to study the Quark-Gluon plasma, the primordial fluid of creation, without needing to recreate the Big Bang itself.
2. The silent survivor. Somewhere in the vast, silent reaches of the deep cosmos, these titans may be waiting for us. They endure pressures and densities that no laboratory on Earth, not even the most advanced supercolliders, could ever hope to replicate. They exist in the shadows of our current technology, silent witnesses to the extreme physics that governed the dawn of time. According to theorists at JPL and the Max Planck Institute, discovering just one quark star would revolutionize our entire understanding of how matter and gravity interact at the most fundamental level.
3. The universe's true self. If quark stars do not exist, then that primal state of freedom lasted for only a fleeting heartbeat before vanishing forever into the annals of history. But if they are out there, it means the universe has never truly let go of its past. It means that hidden within the crushing grip of gravity, the cosmos is still holding on to a piece of its original self, a relic of the beginning, still beating in the heart of a star. In the end, the quark star is the ultimate proof that in this universe, nothing truly beautiful ever truly disappears.
Thank you for joining Knocklick Studio on this journey through the extremes of space and time. If you found this exploration of quark stars fascinating, please give this video a like, share it with fellow space enthusiasts, and subscribe to the channel. Your support is the greatest motivation for me to keep diving into the mysteries of our universe.
Thank you so much for your patience and for being part of our community. I'll see you in the next exploration.